Earthquakes everywhere. Here on Earth? No, all over the solar system. We are Earthlings, and as such we know well the sensation of suddenly feeling shaken by a violent earthquake. But this phenomenon, so familiar on our planet, is by no means an Earth exclusive. Our solar system is a decidedly more eventful place than we might think, with seismic activity manifesting in surprising ways on numerous celestial bodies. Earth, with its millions of annual earthquakes, most of which are too weak to be felt, represents a special case. It's the only planet known so far to have fully developed plate tectonics. But this doesn't mean that other worlds don't have their own ways of trembling, shaking, and vibrating. In this cosmic journey, as always organized for you by the Insane Curiosity channel, we'll explore how seismic phenomena manifest throughout our solar system. From the sound vibrations of the sun to the recently discovered mysterious marsquakes, all the way to the peculiar seismic waves that travel through Saturn's rings. Are you ready to be amazed once again by the cosmos' oddities? Then keep watching. Our journey begins with the star at the center of the solar system, the Sun. You might not think of the Sun as a seismic object, but this enormous sphere of incandescent plasma continuously pulses and vibrates at different frequencies. The study of how vibrations propagate through the Sun, called helioseismology, and through other stars, astroseismology, teaches us a great deal about the internal structure of stellar bodies. The Sun is traversed by harmonic acoustic waves that resonate through its massive body. These solar sound waves have been converted into frequencies audible to humans by the Stanford Solar Center, offering a truly unique auditory experience, the song of our star. These vibrations are not just a curious phenomenon, but represent a fundamental scientific tool for understanding our star's interior, its density, composition, and the energy transfer processes occurring in its depths. We continue our journey with Mercury, the smallest planet closest to the Sun. In 2016, analysis of data from the MESSENGER mission, Mercury Surface Space Environment Geochemistry and Ranging, revealed a surprising discovery. Mercury is shrinking. Small thrust scarps that cross numerous craters have been identified on its surface. The position of these geological formations suggests that the planet is tectonically active today, precisely because it's undergoing a contraction process. This shrinkage is due to the cooling of the planet's core. As Mercury's interior cools, it contracts, causing the formation of these scarps on the surface. It's like an apple that, as it dries, develops wrinkles on its skin. According to studies, Mercury may have shrunk by about 7 kilometers or 4.3 miles in diameter since its formation. Mercury's tectonic activity is evidenced by a network of ridges covering the entire planet, some of which exceeded 300 kilometers in length. One of these formations, called Santa Maria Rupes, is a striking example of how compressive forces have fractured the surface, pushing parts of it on top of each other. Mercury ceased being tectonically active about 3.7 billion years ago, but traces of this ancient activity are still clearly visible on its surface, telling us the story of the planet's progressive cooling and contraction. And we've arrived at Venus, which, from a tectonic standpoint, continues to be a real puzzle for scientists. Currently, Earth's twin planet doesn't seem to possess tectonic plates, and in fact may never have had them. Despite this, its surface shows numerous recognizable tectonic features like faults and folds. These formations, however, could derive from processes different from plate tectonics, such as mantle convection or volcanic activity. So far, we haven't detected Venus quakes, but scientists hypothesize that we might be able to detect them remotely by observing how their vibrations propagate through the planet's dense atmosphere. Venus shows evidence of past tectonic activity, with areas where the surface has been stretched and fractured, and other regions where it has instead been compressed and wrinkled. Scientists are still debating the type of deformation that might occur in Venus's interior and how this might be connected to the features observed on the surface. The fact that Venus is a planet as large as Earth and has an interior that is still hot suggests there might still be some form of ongoing tectonic activity, even if very different from Earth's. And here we are back home, or almost. We've arrived on the Moon. Our natural satellite is a seismically more active world than one might think. This has been known since the time of the Apollo missions, when Buzz Aldrin positioned a seismometer in the Sea of Tranquility on July 20, 1969. Subsequently, the Apollo 12, 14, 15, and 16 missions installed similar instruments, creating the first extraterrestrial seismograph network that operated until 1977. This network of seismometers, extremely sensitive for those times, recorded over 12,000 seismic events in 8 years of activity. Thanks to this data, we discovered that the Moon experiences 4 distinct types of moonquakes. Deep earthquakes, 300 to 800 kilometers, or 186 to 497 miles depth, caused by tidal stretching due to Earth's gravitational attraction. They occur with monthly regularity, reaching magnitudes up to 2.5 on the Richter scale. About 3,000 of these events are recorded each month, concentrated in about 30 well-defined seismic foci. Impact vibrations, generated when meteorites strike the lunar surface. During the Apollo network's operation, 1,700 meteoritic impacts were recorded. One of the most significant occurred on May 13, 1972, when a meteorite of about 1 ton hit the Moon at a velocity of 15 kilometers per second, or 9.3 miles per second, creating a crater 3 meters or 9.8 feet in diameter and generating vibrations equivalent to 200 kilograms or 441 pounds of TNT. Thermal earthquakes, caused by drastic temperature variations between lunar day, 130 degrees Celsius or 266 degrees Fahrenheit, and night, minus 170 degrees Celsius or minus 274 degrees Fahrenheit. These events, thousands per year, occur mainly at lunar dawn, when the rapidly heated surface expands, creating small fractures. They are surface events with magnitudes usually below 1.0. Shallow earthquakes, 20 to 30 kilometers or 12 to 19 miles in depth. Strong, prolonged, and of still mysterious origin. They are the most powerful on the Moon, with magnitudes up to 5.5 and can last up to 10 minutes, compared to the typical seconds of terrestrial earthquakes. In the period 1969 to 1977, only 28 were recorded, mainly in regions like Mare Crisium and Mare Serenitatis. One theory suggests they might be caused by the continuous cooling and contraction of the lunar crust. A unique characteristic of lunar earthquakes is their long duration. On Earth, seismic energy is quickly absorbed by water-rich rocks, while on the Moon, where rocks are dry and highly fractured, seismic waves continue to bounce for a long time. A shallow lunar earthquake of magnitude 4.0 can make the Moon ring like a bell for over an hour. The Moon has not been tectonically active for about 3 billion years. However, evidence of its ancient activity is still visible in the form of faults, such as Rupes recta or straight wall in Mare Nubibium, a scarp 110 kilometers or 68 miles long and up to 300 meters or 984 feet high, or Rupes Kochi in the Sea of Tranquility, where the surface has been fractured and compressed by tectonic forces. Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel. Click on the bell, you'll help us to make products of even higher quality. After the Moon, the next obligatory stop can only be Mars. And so we learned that the red planet has also recently joined the list of planets recognized as seismically active. All thanks to NASA's InSight lander, which landed in the Elysium Planitia region on November 26, 2018, and placed an ultra-sensitive seismometer on the ground. On April 6, 2019, it successfully detected the first marsquake, which manifested with an estimated magnitude around 2.5 at a depth of about 30 to 50 kilometers or 19 to 31 miles. In the first 2 years of the mission, until December 2020, the seismometer recorded over 500 seismic events, most of which were low magnitude, between 2.0 and 3.0. The most powerful event, detected on May 25, 2020, reached a magnitude of 4.2, quite a shake. Regarding the geographical distribution of marsquakes, The mission then revealed two main seismically active zones. Cerberus Fossae, a region characterized by a series of tectonic fractures located about 1,600 kilometers or 994 miles east of InSight's landing site. Here, the most powerful earthquakes occurred. Olympus Mons and Tharsis Montes, the largest volcanic area in the solar system, showed signs of low-intensity seismic activity, possibly associated with deep magma movements. A distinctive characteristic of Martian earthquakes is their duration. Due to the highly fractured but dry crust, seismic waves propagate with less attenuation compared to Earth, making events longer. A Martian earthquake of magnitude 3.0 can last up to 10 minutes, compared to 10 to 30 seconds for an equivalent terrestrial event. The InSight mission concluded its operations on December 21, 2022, after 4 years of activity, when dust accumulated on the solar panels reduced available power to insufficient levels. During this period, the seismometer recorded a total of 1,319 marsquakes. The collected data allowed scientists to put together the first detailed models of the interior of Mars, which helped reveal that Mars possesses a thinner crust than expected, 24 to 72 kilometers or 15 to 45 miles, a silicate mantle extending to about 1,550 kilometers or 963 miles in depth, a liquid core larger and less dense than previously hypothesized, with a radius of about 1,830 kilometers or 1,137 miles, more than half the planet's radius. And after Mars, it would be Jupiter's turn. But you don't have to be a planet to have tectonic activity. Some moons in our solar system indeed show signs of intense geological activity, and in some cases, this activity far exceeds that of any planet. Io, Jupiter's volcanic hell. The most spectacular case is represented by Io, the innermost of Jupiter's 4 Galilean moons. Io is the most volcanically and seismically active body in the entire solar system, with over 400 active volcanoes and sulfur plumes rising up to 500 kilometers or 311 miles high. The source of this incredible activity is not residual heat from formation, but tidal heating. Io orbits Jupiter at a 2-to-1 orbital resonance with Europa. Every 2 orbits of Io correspond to one of Europa, and this creates continuous variation in the gravitational intensity that Io experiences. The slightly elliptical orbit causes the Moon to continuously deform. When it's closer to Jupiter, it's compressed more. When it's farther away, it expands. These tidal deformations, which can reach 100 meters or 328 feet in amplitude on the surface, generate enormous internal friction that keeps Io's interior in a molten state. The power dissipated by this tidal heating is estimated at about 100 terawatts, equivalent to 200 times the world's energy production. The Voyager, Galileo, and Juno missions have documented volcanic eruptions with temperatures reaching 1,800 degrees Celsius or 3,300 degrees Fahrenheit, hotter than any modern terrestrial volcano. In 2001, the Galileo probe recorded the eruption of Sirte volcano, which produced a lava flow 60 kilometers or 37 miles long in just a few weeks. Io's volcanic activity is so intense that it completely redesigns the surface in geologically brief times. No impact craters are visible because they are constantly covered by new lava flows and volcanic deposits. It's estimated that the entire surface is renewed approximately every million years. And what about Saturn? Only recently have we managed to understand that the second most massive planet in the solar system possesses a unique system of natural seismometers, its majestic rings. Some undulating structures in Saturn's rings prove to be sensitive to the planet's gravitational field. Vibrations within Saturn propagate into the rings as waves, ripples, and twists, similar to an earthquake making piano strings vibrate. Recently, this type of ring seismology has allowed scientists to precisely determine Saturn's internal structure and measure the length of a Saturnian day for the first time. Data collected by the Cassini probe during its passage through Saturn's system revealed that waves in the rings can tell us much about earthquakes and oscillations occurring inside the gas giant. It's as if the rings function as gigantic seismic detection instruments, translating the planet's internal vibrations into visible waves. But even at the margins of our solar system, we find evidence of geological activity. Pluto is currently geologically active. Data from NASA's New Horizons probe, when it crossed the Pluto system in 2014, revealed a complex set of geological features, including faults. There's no evidence of transform faults or comprehensive tectonics, but it's likely that Pluto's surface is undergoing stress fractures as a liquid water ocean partially freezes and thaws beneath the icy crust. This geological activity on such a small body so distant from the Sun is surprising and suggests that internal processes can remain active much longer than scientists initially thought, especially when materials like water ice are involved, which have much lower melting points compared to silicate rocks. In short, our journey through the seismic solar system shows us that geological activity is much more widespread than initially thought. From Mercury shrinking to newly discovered marsquakes, from solar vibrations to Saturn's seismometer rings, to Jupiter's moon ice plates and Pluto's geological activity, our solar system is a dynamic and continuously evolving place. Each celestial body has its unique history and particular tectonic characteristics. Larger planets like Venus, Earth, and Mars are large enough to have remained hot inside and still have some form of tectonic activity. Smaller bodies like the Moon and Mercury have cooled more and are no longer active, but their surface features tell of a geologically vibrant past. The study of earthquakes and tectonic activity on other worlds is not just scientific curiosity. It helps us better understand the fundamental processes that shape planets, including our own. Furthermore, understanding seismic activity on other celestial bodies will be essential for planning future human missions, particularly to the Moon and Mars. As we continue to send increasingly sophisticated missions throughout the solar system with seismometers and other precision instruments, our understanding of those cosmic phenomena will only deepen, revealing a solar system even more vibrant and dynamic than we can imagine today. So the next time you hear about an earthquake, remember that this phenomena is not an Earth exclusive, but part of a wide range of geological activities that unite many members of our solar family in a cosmic, seismic dance.